So in the last few sections, we've been talking about how exponent laws interact with multiplication and how they interact with division. And now we're going to explore what happens if an exponent becomes negative. So just a quick few logical exercises to try and sell you on this. If you started with x cubed and you divided it by x, and we were doing this in the last section, that thing there is x times x times x with an x in the bottom. And one of those x's divides out one of those x's, and I'm left with x squared in the top. So pretty straightforward, not complicated. I'm going to do this again, but I'm going to start with x squared divided by x. Now that is two x's on the numerator, one in the denominator. One of those divides one of those, and you're left with x to the 1, because there's one x up there. I'm going to keep this pattern going. Instead of x3, x2, I'm going to put x to the 1 over x. Well, that's just an x over an x, and those two things divide each other out, and anything divided by itself gives you 1. Now, I'd like you to look at what's happening here with these exponents. X squared, x1. This here, if you follow the pattern, that should be x to the 0. 2, 1, 0. Now, that's a little weird fact right there. And I challenge you to pick up your calculator and give it a try. If you type in 3 to the exponent 0, you'll get 1. If you type in 10 to the exponent 0, you'll get 1. If you type in pi to the exponent 0, you get 1, etc. Anything to the exponent 0 is worth 1. Just going to write that down for you. Hope my head's not in the way. Exponent. No. Exponent is worth 1. Okay. And it's because of this idea here, right? That if you put an x over an x, those two things divide each other out, leaving 0 x's behind. But this process doesn't eliminate the fraction completely. It's just a thing divided by itself, and that's worth 1, not nothing. Now I'm going to continue this pattern. I had a cube on top and 1 on bottom, a square on top and 1 on bottom, 1 on top, 1 on bottom. I'm going to try 1 on top, 2 on the bottom. Now, if you simplify that, it's 1x up here, 2x's down there. That divides that, and I'm left with 1 over x. If I do it again as a cube, one of these divides one of those, and I have 1 over x squared. Now, looking at this pattern I've been building here, though, this over this left me with x squared, right? 3 of these minus 1 of those is 2. 2 of these minus 1 of those is 1. 1 of these minus 1 of these is none. Now I've got one of them, subtract 2 of them. If you do 1 subtract 2, you end up with negative 1. Like that. And if you look at this pattern here, I'm just reducing the number of x's in each term, and watch what's happening to my answers. This drops by 1, by 1. If you're at 0 and you need to drop another, you're at -1. Here, was at -1, I need to drop another one. Now I'm at -2. And you end up with this little thing happening here, where dividing by 2 powers of x could be notated as writing x to the exponent -2. This negative here then means that you're using an exponent to imply division, because we're dividing by these things, instead of repeated multiplications. Now that's handy because multiplication and division are the same operator. They're just forwards and backwards of each other, like squaring and square rooting. So if you have a handy notation to shortcut multiplication, you should be able to use that same notation to shortcut a division. So I'm going to clean this off, and we're going to try playing with this a little bit. So if I see a normal number sitting there and it has a negative exponent on it, what that's telling me is that I'm not multiplying by this number, I'm actually dividing by it. So that thing in its fraction form would look like 1 divided by 9, because instead of multiplying by this, you're dividing by it. If I had something like this, the negative tells me that I'm dividing by 2, and the 3 tells me I have to do it 3 times. So I'm going to have to divide by 2, and then again, and then again, which is the same as dividing by 8. 2 times 2 is 4, 4 times 2 is 8. Now, if you want to sort of shorthand this, the fact that there is a negative told you to put your answer in the denominator. Put in denominator. And the exponent just behaves as normal. So if you're handed something like 5 to the exponent -2, well, you see a negative, and so the negative tells you you got to put this answer in the bottom of a fraction. And 5 squared is just 25. So this thing here is telling you to put the number 25 in the denominator of a fraction. And so one more here, 3 to the -4. Well, I know that 3 to the power 4 is 81. Because 3 times 3 is 9. Times 3 is 27. Times 3 is 81. And I see a negative exponent, so I'm going to have to put an 81 in the denominator of a fraction. Which is another way that you can sort of convince yourself that fractions were never real in the first place. They were just things with negative exponents, which are just divisions that are waiting to happen. So if you find fractions uncomfortable, you can always switch to the negative exponent notation, and then you don't have fractions at all. I'm going to clean this off. We're going to try applying it to some messy variables and see how that goes. Okay, so I have an expression here that is a bunch of letters and numbers in a fraction. And I want to stop writing it as a fraction. I want to start writing it as negative exponents. So I'm going to look at this stuff up here, this 3x squared y. Now, it's not in the denominator, so it's just minding its own business. I don't have to do anything to that. But this part, the 2pq3, all of that stuff is in the denominator of that fraction. So I'm going to build a bracket. I'm going to put all that stuff in there. And I'm going to put it to the exponent -1 so that I know it should be in the denominator. Now from there, I can apply the exponent laws that we were doing before. This exponent applies to this and this and this because it's all multiplying in there. So I have 3x squared y, 2 to the exponent -1, p to the exponent -1, and q to the exponent -3. If you remember, this particular exponent law said take whatever's in there and multiply that in. And if you look at what's written here, I just took a 2 and put a negative on it. I just took a p, put a negative on it, and I just acknowledged that this q to cube was in the denominator was a negative. And so I was able to write this fraction as this expression, and I don't have any I don't have any fractions in it. So what if you have one like this? I have a 5, and then x squared, and a y cubed, and a 4, p to the 5, and a z. And the whole thing is to the exponent -1. Well, when we did this before, you applied the -1 to all the things in there, but I'm going to take this and I'm going to write it like that first. So I have the top 5x squared y cubed, and it is to the exponent -1. And I have this stuff down here, 4p to the 5z. Now, this is where you have to be careful. This was already in a denominator, so it's to the exponent -1 because it's in a denominator. And then an extra -1 was applied to it because of this bracket. Like that. So if I go through and I work this out, 5 gets a -1. That's x to the -2. That's y to the -3. Now, I'm going to look at these two exponents there. Your exponent laws from the last video, like if you had x squared to the power 4, that meant x to the 8, right? This times this gives you that. So now I have two negative exponents I have to multiply there. Well, -1 times -1 is 1. It's gone. So I would end up with 4p to the 5z to the exponent +1. -1 times -1 is +1. And generally with exponents, just like this z here, there's an exponent 1 on this z, but we don't bother writing it because I can already see there's already one z. So this isn't really necessary. It's implied just by the fact that this exists. Now, if you look at these pieces, that piece, that piece, that piece are all in the denominator. So 5 to the -1, x squared, y cubed. This piece doesn't have a negative exponent on it anymore. So this piece is up in the top. This piece is up in the top. And this piece is up in the top. Now, if you look at this fraction and that fraction, everything that was in the numerator is now in the denominator. Everything that was in the denominator is now in the numerator. So it looks like applying a negative exponent applying negative exponent to a fraction flips it. So whatever was on top and bottom before, now they've switched places. So I'm going to clean these off, and we're just going to do some things that look like what's in the example problems. So to get you good at this notation, you have to be able to flip-flop back and forth between the fraction type notation and the negative exponent type notation. And I think this word negative is on my forehead right now, which, suiting my mood many days, is probably appropriate. But if I'm looking at this, when it says write this without a fraction, I can eliminate the fraction notation if I just use negative exponents. So just to get used to being able to transition between them, that 5 is in the numerator, it stays a 5. This x squared is in the numerator, it stays as x to the positive 2. This y cubed is in the numerator, it stays as y to the positive 3. This 4 is in the denominator, so it will be a 4 to the exponent negative 1 to show that it should be down in the basement of that fraction. This p to the 5 will be p to the negative 5 to show that it should be in the denominator. And this q should end up as negative 7 to show it should be in the denominator as well. So I've taken this expression, which was written in fraction form, and I have rewritten it without needing the fraction bar. If we go the other way, take an expression where there's no fraction bar, but there are negative exponents all over the place, and write the expression without those negative exponents, I just have to go through all the pieces. All the things with positive exponents stay in the numerator, all the things with negative exponents go in the denominator. So I've got a 3, no exponent at all, up it goes. X to the negative 4, that's an x to the power 4 in the denominator, because it was negative. P to the 5, that's a positive exponent, it belongs in the numerator. Y to the 8, that's a positive exponent, it belongs in the numerator. 7 to the negative 3, well, that's a negative exponent, so that 7 cubed belongs in the denominator. And just good math habit, you try to write the numbers first. Z to the negative 2, that's a negative exponent, so it goes into the denominator. And there you go. I have taken this expression and I have eliminated all the negative exponents and written it in its fraction form. So if you have a complicated expression, you need to simplify it. I mean, this looks just like the expressions we had in the first 2 sections of this. This notation says that everything in this bracket, because it's all multiplied together, is going to experience this exponent negative 3. So a 3 with an exponent negative 3 on it just looks like that. X squared with a cube on it would be x to the 6. And a positive and a negative together makes a negative number. So this thing, when it has a negative applied to it, ends up with a negative exponent. Y to the negative 5 to the exponent negative 3. Well, 5 times 3 is 15, and a negative times a negative is a positive. So that stays as y to the positive 15. Z to the 7 to the exponent negative 3. 7 times 3 is 21, and a positive times a negative is a negative. And p to the negative 2 to the negative 3. 2 times 3 is 6, and a negative times a negative is a positive. So I have p to the 6th. So I have successfully applied the exponent -3 to all the stuff inside there that needs it. And I have this line here that's written in the negative exponent notation. Now that's fine. I mean, you're done. It may be, depending on your circumstances, more useful to see this in fraction form. So we're just going to finish this problem by taking all these negative exponents and writing it in the fraction form so you can see both lines, and then in the alleged application that's coming up later, you'll have both forms to choose from. So if I see negative exponents, I'm going to need a fraction line because some of these things are on top, some of them are in the denominator. I see 3 to the -3, well, negatives go down here. X to the -6, negatives go down here. Y to the 15, that's up in the positives. Z to the -21, negatives go down here. P to the 6, that's positive, it goes up there. All right, so if you can apply an exponent like that, then you can generate a fraction like this. If there was another one being multiplied here. Ooh, that's going to be big. I'm going to just do this same thing. I'm going to apply that -2 to everything in the bracket. So 4 to the -5 to the -2. 5 times 2 is 10. A negative times a negative is positive. Y cubed to the -2. That's y to the -6. X squared to the -2. That's x to the -4. Now, if you look across this line, it's hard to see which things divide each other out. And you can just apply the exponent laws, right? Y to the 15 and y to the -6. 15 and -6 should be 9. You can do that if you're going to work in this line. But if you want to be able to see things on top and bottom that divide each other out, I'm going to have to write this in its fraction form. So get myself a line. I have 4 to a +10, that goes on top. I have a y to the -6, that goes in the bottom. I have an x to the -4, that goes in the bottom. Now if I look across here, I have 15 y's on top and 6 y's on the bottom. Some of these are going to divide out all of these, leaving 9 of them behind. So I will only have y to the 9 in my numerator. There's nothing dividing out the p's, so p to the 6 kicks around. There is nothing dividing out powers of 4, so the powers of 4 stick around. There is nothing dividing out the power of 3, so it sticks around. I have 6 powers of x here and 4 powers of x here. That's a total of 10 powers of x. And there's nothing dividing out this z to the 21. So even if there are two pieces that have negative exponents on them, you just work it out piece by piece. Maybe flip it into the fraction form if you find that easier to understand. And then you combine those fractions just like we've been doing before. So I have here a rational function, and we've done some algebra on these already, but this operator felt a little weird compared to the other ones, and the way you had to handle it felt a little weird compared to the other ones. And that's because we didn't have this tool to write this in a way that looks like the other functions. So I'm just going to do that now. I have a dividing line. So anything that's under here, right, this stuff, the argument of that function is all in the denominator of a fraction. So if I were to write it that way, 4x minus 5, to put that in the denominator, I need an exponent -1. This 20 doesn't have a negative exponent, so it goes in front with a positive exponent on it. And this +2 is just kicking around. Now this is the format that all of the other functions were in. External modifiers, an operator, and an argument. And you can see it laid out that way if you use the negative exponent notation. So I'm going to solve this one using the exponent laws. I want to find when this is 3. So I make 3 equal this. I'm gonna put this in brackets just so we can see there. Now your algebra skills, right? You would do that first, then that, then that, then that, then that. So this is the thing I have to undo first. I'm going to subtract 2 from both sides. 3 minus 2 is 1. And I have to get rid of this now. So it's connected with multiplication. Also, it's a 20. So I need to do 1 divided by 20. And now I've got to the place where I have this operator that I have to break. So when you came to this line and it was a square, you would square root the other side. When you got to this line, if it was a logarithm, you would put an exponential on that side. If you got to this point and it said sine of whatever, you'd use arc sine on the other side. So every function has an opposite, a way of undoing itself. This one does too. And it's just in the exponent laws. We did it a minute ago. If I take this side and I put the exponent -1 on it, exponent laws say I have to multiply this by this. And -1 times -1 is 1, which will end up eliminating that exponent. You can't just do it on the right side though. You have to do it on the other side as well. So this pink exponent -1 has been neutralized by the blue exponent -1, leaving only 4 the x minus 5. Now here I have a fraction inside an exponent -1, and that told you to flip it. Right? Anything that was in the denominator will now be in the numerator. Anything in the numerator will now be in the denominator. So this fraction ends up as 20 over 1. Now that just says 20 divided by 1, and 20 divided by 1 is just 20. So by writing this thing in negative exponents, I was able to use an anti-function in order to deal with this algebra instead of having to cross multiply or distribute x's or any of that stuff. So if you can master this notation for solving these things and using the algebra, it makes the work a lot easier. So just to finish, I need to divide by this 4. 20 divided by 4 is 5. And I have to add 5 to both sides. Therefore, x is 10. And if you want to check it, right, you put your 10 here. Ten minus 5 would be 5. 4 times 5 is 20. 20 divided by 20 is 1, and 1 plus 2 is 3, which is what I was asked to solve for. So there are a few questions like this in the practice problems because I want you to take a stab at using this notation. But then after that, going forward, you are free to choose whether you want to use the negative exponent notation or if you want to try and use the cross multiplication technique for solving rationals.